Hi again, everybody, and welcome back. We're continuing notes on Chapter 5 on forces and Newton's laws, and this is going to be example 3, our Jack and Jill pail problem. I'm going to modify this problem a little bit. I think it'll make it a little bit easier. We're going to take some things and change them just a little bit. One thing I do want to point out before we start, however, is we're going to be starting to talk about forces that we haven't really defined very well right yet. For example, this force right here, W, also known as the weight force, or in this case, it's also called, the weight force is called Fg. In fact, let's just change that right now. That's going to be, I'm going to call it Fg, okay? We're probably going to give it a different name a little bit later. That is the force that is caused, or that is created by gravity. Gravity applying its acceleration on this mass and giving it a weight, which is why if you applied it to a scale, it would register some sort of a weight. That's the force that is being directed downwards because of gravity. All right, but we're going to change one other thing as well. All right. By the way, this part of the problem, this segment, is we're only going to do part A. All right, because with me explaining it and everything, it's going to take probably a little while. And if we did the whole problem together, it might take it might be a pretty long video. All right. So the idea is that part A. We want the pail to accelerate upwards and upwards only. Upward only. Now, if you look at these forces right here, they're at angles. All right. So that means they both have an upwards component. Let's just go ahead and draw those in real quick. I usually do my vertical components in blue and my horizontal components in green. Oh wow, this is way too long. Sorry about that. Like that. And this is our horizontal components right here. Okay. Like so. And they're at some angle. We're given what force 1 and force 2 are, and so we can find the x and the y components. But the problem is that we're being asked to find, all right, in order for this pail to not slosh backwards and back and forth side to side, what angle from the vertical should Jack, and Jack is here on the left-hand side, what angle from the vertical should Jack hold or apply his force to the pail? It says right here, Jill is applying it at a force, or at an angle of 28 degrees from the horizontal. Normally, if you hold a pail, you apply your force straight up in the air, right? They're both at a little bit of an angle. But the problem here is, and we don't really like this very much, the angles are based from the vertical, and we don't like dealing with that. So I'm going to change this a little bit so it makes our life a little bit easier. First of all, we're going to say Jill's force is exerted at an angle of not 28 degrees with the vertical, horizontal. Okay, what would that be with the horizontal? So if this is 28 right here, what should this be if they're complementary angles? Well, that should be 62 degrees, right? 62 degrees. So I'm actually going to draw Jill's stuff in orange right here. So here's Jill's force. Can't really draw on the line very well. Jill's force 2. Like that. Force 2. And her theta 2 is going to be 62 degrees, which means we don't care about Jack's, where is it, angle theta? Okay, yeah, so we don't want Jack's angle from vertical either. We want his from the horizontal too. Again, if you know the horizontal angle, you can find the complementary vertical angle, but let's just stick with horizontal, all right? So this right in here, I'm going to do Jack's in like this light blue color. All right, so that's Jack's force 1. What we're really solving for is theta 1 right there. That's what we want to know. The idea is that these forces, the x component of Jill's force and the x component of Jack's force, are going to balance out. Okay? So we've got our angles. We're going to solve for the angles based from the horizontal, not from the vertical. I think that'll make it a little bit easier, even though it required a little bit of extra legwork up front. Okay. So if the pail is going to be accelerating upward only, then this is what must be true. It's not going to be accelerating to the right or to the left. So we must be able to say then that the net force in the x direction equals 0 newtons. Here's our first example, really, of where you can have forces in a certain direction. And there's certainly some forces or components of forces in the x direction, but there's no net force right there. So remember, when we say there's no net force, we're not saying there's no forces. We're just saying that they all add up to 0. So it's kind of like saying this. If there's no acceleration in the x direction, there's no net force in the x direction. It's like saying this. The net force in the x direction is, which one should we call positive? Force 2x or force 1x over here? I drew that kind of far away, didn't I? Force 1x. Well, we probably call this one our positive because we're used to left to right being positive and the right to left being negative. So it's like saying force 2 in the x direction minus force 1 in the x direction equals what? Equals this right here, because they're both statements about the same thing, right? The net force is 0. And the net force is these two component forces acting against each other. So we're going to have to say that whatever the x component of Jill's force is going to have to be equal and yet opposite to the x component of Jack's force. That should help us find Jack's angle theta. Okay? So let's find Jill's x force. So let's say for Jill, okay, her force 2 in the x direction. That is what? Well, we have the full magnitude of her force, and her full magnitude of the force that she's applying is going to be 11 newtons, right? So the x component is going to be the full magnitude times the cosine of theta, right? So that's going to be 11 newtons times the cosine of, what is that angle with the horizontal? It's going to be 62 degrees, right? So we're going to find out what Jill's x component of her force is. I'm going to write that in green because I'm going to keep that in green. 11 cosine of 62, I get 5.2, all right? 5.2 newtons. And that's what this is right here. That was gotten by taking the x component of Jill's 11 Newton force at 62 degrees. Okay, so that means then that Jack's force, and I'm going to do him in light blue, since Jill's 5.2 Newton force has to be equal and opposite to Jack's x component of his force, because he's force 1 right there, then that means for Jack, all right, the x component of his force has to be F1x has to be 5.2 newtons, or I should really say negative 5.2 newtons. You can't have a negative magnitude, but you can have negative components, all right? And so the x component of Jill's force is positive, the x component of Jack's force is negative. All right, well, this is very helpful because now we're going to know what Jack's x component of his force is. Negative 5.2 newtons. Okay, well, if we know that Jack's full force, that is the full magnitude of his force, equals 7 newtons, and we know the horizontal component of it, we should easily be able to find the theta that his force makes with the horizontal. How do we know that? Well, we have the adjacent and the hypotenuse, right? All right, so if we say that like we said with Jill, the x component is the magnitude times the cosine of theta, we should be able to say with Jack that F1 in the x direction, looks like a y, doesn't it? In the x direction, sorry, my stylus is not very precise. Force 1 in the x direction equals the full force 1, the full magnitude, force 1 times the cosine of theta. All right, so that means a cosine of theta, or I should say theta 1, right? That's Jack's force. Cosine of theta 1 is going to be then Jack's x component, force 1 in the x direction, all divided by what? Well, the full magnitude of his force, because we divided that force 1 down, okay? So what are we solving for? We're solving for this angle theta in here, all right? Well, with the cosine of theta equals this ratio, then that means theta itself should be theta 1 equals the inverse cosine negative 1, of the x component over the full magnitude. Well, that's going to be 5.2 newtons. And if I can get my right color here. There we go. 5.2 newtons, or you could put negative 5.2, doesn't really matter. We did technically say that it is in the negative direction. Divided by the full magnitude of its force, that's going to be 7 newtons right here. All right, so this is solving for part A, and this is going to wrap up the section right here. What is that angle that Jack has to pull at such that his x component balances out Jill's x component and there's no net force in the x direction? Well, we're going to find that out right now. So the inverse cosine of 5.2 divided by 7, that's going to be 42 degrees. 42 degrees, you might say north of west or above the negative x-axis. Either way, that's going to be our angle right here. Now again, remember the original problem said, what is it from the vertical? Well, if you wanted to find it from the vertical, if this was 42, then this would be 90 minus 42, which would be, I think, 48. All right? But all we're going to care about in this problem is just the angle from the horizontal that Jack is going to be pulling at. Okay? So that's our answer. 42 degrees north of west. So really quickly, to recap, what we did was we found Jill's took her full magnitude and turned it into an x component. We stated that our x components have to be equal and opposite. Then we said, okay, Jack's x component must be the same magnitude but opposite in direction as Jill's. And then we did a little bit of trig and figured out what the angle has to be between his x component and his full magnitude in order for those proportions to be true. All right. So that's going to be it for the first part of example 3, and I'll see you on the next segment for part B. Thanks for following along. I'll see you on the next one.